So, how did the universe begin? What happened 13.8 billion years ago? And will we ever be able to figure this out? So, welcome back to the Fundamental Why. And today we have an episode on the birth of the universe. So, hi, I'm your co-host Sahil.
I'm your other co-host, Cary, and first off, we're going to introduce you guys to the theme. So once again, it's about metaphysics, but we're going to look at it from a different perspective this time. We're going to go back all the way to 13.8 billion years ago, to where it all began. Reality, the universe, everything. The birth of our universe, you can say.
Yeah, definitely, I would agree. And now, just to give you a bit of a overview of what we'll be covering, first we'll, in our current and proposed theories section, we'll talk about the simulation hypothesis, as you might have guessed, the Big Bang. And then we'll kind of go into a bit of philosophical interpretation with cause and effect and what that can mean in terms of the Big Bang. So let's just step back and think about the Big Bang, or more, think of it as the birth of the universe. Well, when we ask questions about, where did everything come from? Where did society come from? Where did our creativity and, just everything around us, where did that come from? Well, turns out that the Big Bang is the ultimate answer. It is the source of everything. And think about what we're made of. We're made of iron, carbon, oxygen. We're made of star stuff. These were the elements forged at the center of stars that were created by the Big Bang. So now let's kind of move on to our current and proposed theories.
So I'd like to start with the simulation hypothesis. So you guys might not have heard about this before. It's a more abstract way of thinking about the birth of the universe. It's first proposed by philosophers Nick Bostrom and David Chalmers, and it basically proposes that none of us are real. We're not real, you guys are not real. The whole recording space we're in isn't real, the universe isn't real. We're all just pieces of code in a giant simulation run by an alien supercomputer or by a higher intelligence alien species. And so the birth of the universe would really be more like an initiation sequence of the simulation we're currently in. It wouldn't mean anything physical or real. Now, you might be asking, what is the evidence or reasoning behind such an idea? Well, currently there's no actual physical evidence that we're in a simulation. Scientists are trying to figure that out. But there's a bit of logical reasoning that might help you guys better understand. So first of all, we have to realize that uh, different intelligent species would want to run simulations of anything, for example, of our world, of other species as well. We can see that in our current society as well through different simulation games like the Civilization series or other different simulation type models like software CAD, where you can simulate physics laws through the computer. And secondly, if an alien species were to be able to simulate life, then there would be so many simulated beings that they would greatly outnumber any actual physical beings. So if you take any random conscious entity, it would most certainly be in a simulation. So we're in a simulation, basically, I guess. But let's move on to a more optimistic view and the more generally accepted theory of the birth of the
Yeah,
universe.
of course. And now that is the Big Bang, as many of you might have heard of. And so yeah, this theory tells us what the universe was like in its very earliest moments. And I'll start off by saying it does not tell us what caused the universe, what happened before it, or what happened exactly at the moment that the universe was born. But it only tells us what happened right after, like a very, very tiny time frame, which is about 10 to the negative 43 seconds. So quite small. But right after that time period of t equals 10 to the negative 43 seconds, we move on to what the current laws of physics can actually, or what actually becomes relevant and works. So that was the Planck area we just spoke of, where we're fully in mystery, our laws of physics break down. But right after this, we see something called cosmic inflation. This is an exponential expansion of the universe, and you can think of it as from the size of a small atom all the way to the size of a grapefruit in very, very small amount of time. So it's an extremely large expansion there. And then we see after a little bit of time, some of the energy starts to allow for the first particles to be formed. These are the most fundamental ones, like quarks and gluons. And these kind of make are the fundamental building blocks of the protons and neutrons that we're more familiar with. So as we get these protons and neutrons, a little bit of time later, they start to form the lightest nuclei like helium and hydrogen, and even trace amounts of lithium. So this all happens in just the first microsecond of the universe's birth, right? And so that's really surprising. And so you should also know that at this stage, the universe is very energy dense, very hot, almost like a plasma-like state. You can almost describe it like a primordial soup. Um, so in that state, light cannot move very well. It scatters around different electrons, and yeah, light cannot move in a straight path. So the universe was opaque, and like we couldn't actually see through it. But then after 380,000 years after the Big Bang, then the universe cools down enough until it allows for light to finally transmit. And this is when the universe becomes transparent. And there is a special name for this. It's called the recombination era. And this light that just got released is called the cosmic microwave background. We have a special name for that as well, and I'll tell you why that's very important for the Big Bang Theory very short. So now let's go a bit forward in time, about a billion years after the universe. So we have the first galaxies and the first stars that formed, and now fast forward even further, 13.8 billion years later. And here we see the observable universe, Earth all around us, and here we are just asking about how the universe began. So you might think of this as, oh, it sounds nice and great, but how would we ever know that it actually happened, right? Isn't this just all speculation? Well, I kind of wanted to share a few compelling pieces of evidence about the Big Bang. So number one is the CMB I just spoke about, that light that got emitted, that afterglow of the universe. Turns out that we're actually able to detect it, right? So the Big Bang predicted, sure, we might have that, remnant light from this hot, energetic Big Bang state. And now the fact that we can actually measure it and we can actually detect it with our equipment was one of the biggest confirmations of the Big Bang theory. And so yeah, that light is in the microwave range, so we can't actually see it, but we can, of course, with really precise equipment, we can detect it. Um, and the other like piece of evidence that I want to talk about is Hubble's law. So you might have heard of Edwin Hubble and the Hubble telescope. Well, it was Hubble who found out that galaxies are actually moving away from each other. And so the only way for this to happen is if the universe itself is expanding. And so we see the universe, and it's actually accelerating the expansion. It's not just, slowing down or at a constant rate. And so what if we were to backtrack in time? Right, then we would see the universe contract, and according to our calculations, it would keep contracting until 13.8 billion years. And that's at that exact point, 13.8 billion years in the past, we would see it as a singularity. And so Hubble's law tells us that the universe was extremely small, energetic, and very hot and, um, extreme type of environment that the Big Bang proposes. So that's why that's the other piece of evidence there.
Oh, I see. Well, there's actually an interesting actually problem that comes up with something you mentioned. It's related with the CMB radiation. And when we currently measure it as of now, we see that it's the same temperature all across the universe. No matter how far you go away or in which direction you go, it's the same temperature. It's basically in thermal equilibrium in a sense. But this proposes a problem actually, because we normally think the universe is expanding at a constant or exponential rate, then if it's expanding at this rate, the CMB radiation wouldn't have had time to reach the farther parts of the universe in time to transmit heat, energy, or information. And our measurements go against this. They say it's the same temperature everywhere. So do, do you know of the interesting solution that there is to this
Yeah, of
problem?
course. That's actually a really interesting problem, right? And we would expect, there to be small cold patches around the universe. Why is it all, uniform? Well, the solution, it turns out, was cosmic inflation. So that was a relatively modern addition to the Big Bang theory, where, as I said before, the universe expanded exponentially, like very, very quickly, in that small amount of time. And so the reason why it solves it is because when the universe was very small, it's really easy for light and heat to travel around. It's a really tiny universe, so it equilibrates in terms of its temperature. So we see everything uniform in that small state. But our question is, but now once we add in the inflation, the universe is able to expand at a very fast rate. So we whatever that uniform tiny space we had, that's now expanded to a very, very large universe. So it's almost as if the cosmic inflation allows us to preserve that uniform heat and it blows it up almost. Like I almost imagine we're stretching that uniform shape of or uniform fabric of the universe, and now that's the reason why we see heat and light or the heat energy to be uniform around our entire universe, even though it's so large, because it had the time to exchange energy when the universe was small. That's the reason how cosmic inflation solves, and it's really interesting there. And now we also want to talk about our next, I guess, topic here, which is cause and effect, right? So we know what cause and effect means, right? If I drop an apple, the apple hits the ground, right? And of course, it falls is the effect, and the cause was that I chose to drop it, right? But now, what does cause and effect really mean when we're asking, what caused the universe?
That's actually a really interesting question, Sam. What actually caused the birth of the universe? We might have known what happened after it, but what specifically caused it? And there's an interesting topic I would like to bring up. It's a little bit related with philosophy overall, and it talks about cause and effect and its relationships with change and time. So we know from a previous episode that time and change, they're interdependent. Without change, you can't have time. Without time, you can't have change. And cause and effect is essentially the same as change. In order to have change, there has to have been an effect and a cause. So basically, scientists Stephen Hawking and Nick Halbers, they basically said that time didn't exist before the universe. Time emerged from the birth of the universe. So because there was no time before the birth of the universe, there couldn't have been any change or cause because they're all interdependent on each other. They need each other to exist. So this is basically saying that there was no cause for the birth of the universe. It just happened. Now, the reasoning might sound a little bit complicated or confusing, but there's an easy analogy to understand the logic behind this. And let me introduce that to you guys. So, asking what caused the birth of the universe is like asking what's north of the North Pole. Doesn't make any sense at all when you think about it, because north is dependent on the North Pole. So, the cause of the universe would have to depend on time. But if time didn't exist before the birth of the universe, then all of this wouldn't make any bit of sense. But this might be a bit unsatisfying for you guys. Might sound a little bit like an excuse or an easy way out. So let's talk about the more evidence-backed and more physics explanation for the
Yeah,
birth of the
so physics
universe.
does have there's a some cosmologists do have this belief. It's called quantum fluctuations. It might sound like a technical term, but all it is that quantum mechanics. It tells us that when you have empty space, like a vacuum, it's not truly empty. There's still energy and particles that are there, but not in the sense that you're thinking of. What I mean is that energy is allowed to be spontaneously created and destroyed in a very, very, very small time scale. And if that happens, it's almost as if nature never even recorded it. And so that means we're seeing constant, flashes and bursts and disappearances of energy. And so that's what a quantum fluctuation is. And well, why does this relate to the Big Bang? Well, imagine, let's say this whole we just have a void, okay? But there's still in this vacuum, this void, nothing was there except there were still quantum fields that existed. And so these fields, of course, fluctuate in energy. But imagine in there we it's a hypothesis that there might have been a chance, an event where energy could have spontaneously been created at a very, very precise point. So imagine all that energy just randomly being created at that one point, and then it becomes it just starts exploding outward, right? Like the energy at that point, and then we see, the Big Bang and everything else. So that's one idea there, but it's super speculative, and it assumes that the laws of physics existed before the universe, and that's a big assumption that we have to make, I guess, because as Carrie said, nothing if without time, or if there was truly nothing there, then we would never expect anything to change, right? Why should that nothing become something, right? That's the question that I guess we'll talk about in our discussion section that we want to move on to. So yeah, so Carrie, my question here for you, I guess, is did the laws of physics precede the universe? And if not, how could these laws govern the birth of the universe?
I think that's a very interesting question. And I think there's two ways to think about this way. There's the first way, Platonism, and then the second way, empiricism. So For Platonism, we basically like to think that the laws of physics are like exist independently of our universe, so they're not dependent on each other. One can exist without the other. So basically, you can think of it like they're in a different realm, even, or different dimension than what we're currently living in. But there's also empiricism, which is that the laws of physics are just descriptive. They just describe some patterns that we humans see in the universe itself, and we try to categorize them through physics laws. And for me personally, I think that empiricism kind of makes a lot of sense because we want to better understand the natural world, and we use physics as a means to accomplish that. So I think that the patterns have existed and the relationships between different pieces of matter exist past the universe. Like it existed before the universe, but the laws of physics are just a useful tool we have of
Hmm.
understanding the world. Do you have a
Yeah, I like that
another
perspective. I guess
perspective?
you talk about you support a bit more empiricism because laws of physics are more descriptors, right, rather
Yes.
than like real things themselves. I feel like I kind of agree a little more with Platonism. I mean, the way you said it makes it sound like, we just made up like a multiverse like theory where like there's a new realm. But you can also think of Platonism in this way, where um it's not like laws of physics can exist even without the universe in the same way. Let's say we take math, for example.
Yeah.
Say like one plus one equals two. That exists regardless, or if we even have a universe. Like imagine nothing was here, one plus one will still equal two. As long as, I mean, of course, we're expecting that there's going to be someone there to do that calculation. But even if there's no one there, that law still holds, right? So in the same way, one could say that the laws of physics would still hold even without a universe. But as I like your perspective, that's kind of also, I guess, making me kind of rethink what I'm saying is if the laws of physics were like the laws of physics are dependent on how to say this
Like
yeah,
nature of the
yeah,
universe.
yeah. Before the universe existed, like there wouldn't have been any laws of physics, right? And the laws of physics are descriptors. So that means if there's nothing to describe, then do the laws of physics even exist, right? So I feel like we kind of need a middle ground between our two perspectives there, right? Because in a sense, I feel like there's no need for a universe to prove the laws of physics. Like say, for example, gravity, right? Like I feel like gravity could exist without the universe, but we need two masses for gravity to ever, take effect. So in that case, maybe gravity does not exist, right? So you see what I'm saying? There's a bit of a nuance in that in our discussion here,
Yeah,
right?
that's an interesting point
Yeah,
because the laws of physics require like things to actually be present for them to be true in a sense. So if there was nothing there, then I guess they wouldn't exist
yeah,
either. And you also brought up an interesting point about the laws, like they're always true, one plus one is always two. That makes a lot of sense to me. So in your opinion, are laws like physical things or are they just like mental frame kind? Are they actually
yeah.
something
So
physical?
exactly, that's a beautiful question because in some cases they're not physical and in some they are. Let me give you an example. So in the case they are physical, at least we create something called quantum fields, as I talked about for quantum fluctuations. So that you can think of so one could say that it's simply just a construct that we created to describe, say, like, I don't know, an electron. If an electron's like, an excitation of a field, you can think of it as like, if an electron's here, the field has to, spike, I guess. So in that case, a field could truly exist, or it could be a construct, right? We kind of don't know, but in the case where they do exist, then we would say that they could exist regardless of the universe because the fields are always there,
That
right?
makes sense.
Yeah, so that's kind of my perspective on that, on what you're saying there, right? Because but in the other sense, right? I just want to add to that, where the laws of physics are like do not exist, you could say that like for example, I gave you the example of gravity, like gravity requires two masses to be there. So, and it's more of a description, right? Like we're just saying, oh, I see if I drop something and I see the event occurring, I call it gravity, right?
Or
Like
like a
that. Yeah,
relationship.
it's more of a relationship. It's not an actual like thing, I guess you could say. But in contrast, where like a quantum field, I told you about, that is like it's hard to say whether it's just some like just a useful tool we created or an actual physical thing that is there. So there's a bit of a gray area there.
Yeah, I feel like that makes a lot of sense. Like some parts might be like just descriptors. They came about after the birth of the universe, while other parts they've always been there. They're timeless
Yeah,
truths. They
exactly.
always
So
exist.
I guess yeah, there's a bit of a you can't generalize it for all laws of physics because we're not, I guess, at that stage of our understanding.
Yeah, yeah, yeah. We're still
That's
just
quite it.
humans on a giant
Yeah,
rock in outer
exactly.
space.
Yeah. So I guess that was a great discussion. Would you like to kind of move on to our
Yeah,
conclusion to
let's move
wrap
on
up?
to a conclusion, wrap up, and give you guys a few questions as well.
So now let's just summarize this very quickly. Here are some two fascinating, or I guess strange things we spoke about. Number one was the simulation hypothesis. That's a really wild and crazy, I guess, idea that we're all, just us in a simulation, similar to like the Matrix movie. How we're kind of saying the same thing, and also quantum fluctuations. You guys all might have heard of like conservation of energy, right, and stuff. We're saying that that can be violated as long as it happens in a very, very short amount of time that the universe kind of corrects itself. So here, that's also, another fun fact, or I guess a strange fact that, you might not have known before. And also, now just to summarize everything we spoke about, we talked about, the simulation hypothesis, I just said. Also, the Big Bang, I gave you, a bit of a timeline there and some of the piece of evidence. Then we spoke about how cosmic inflation solves like the horizon problem, where why is temperature so uniform all around us? Well, I explained how cosmic inflation solves that. And then we spoke about cause and effect and a more philosophical stance towards like doesn't make it's like nonsense to ask such a question of how the universe was born, or a more physics view of quantum fluctuations as a very speculative yet potential, I guess, idea for that. And then we moved on to our discussion.
Yeah, so me and Sal,
Yeah.
we wanna give you guys the turn to be able to answer a question and think for yourselves now. So we're gonna ask you guys, what do you believe caused the birth of the universe? So we're gonna first start with the more physics standpoint of quantum fluctuation. Random concentrations of energy came and formed our universe, or we can take that's the first option you guys can choose. So let's move on to the second one. That's the philosophical one. It's nonsense to even ask such a question. It doesn't make any sense at all. And thirdly, we have a wild card for you guys. So the third one, we like
Yeah.
to think that there's another all-powerful entity, maybe even a godlike being that came about and created our universe, and that would solve a lot of our problems and paradoxes quite easily. So those are the three options. Make sure to comment down below what you guys believe caused the birth of the universe. Thank you all for
Thank you so
listening.
much.
Yeah,
And yeah,
like and
like and
subscribe,
subscribe
and see
and see
you
you all
all
next
next
time.
time.